All right, let's hit this one. This is 015C Sticky Sneakers Lab Sheet. Okay, let me zoom in a little bit for you if I can. Nope, I can't. Okay. All right, so sticky sneakers. Always read the lab, always read it. It says the appropriate sneaker for an activity should have a specific type of tread to grip the floor or the ground. They say this kind of stuff to you to get you thinking in the mode that will help you understand what you're doing. In this lab, you will test different sneakers by measuring the amount of friction between the sneakers and the table. And remember friction, if you take your hands and you rub them together, and you feel the heat and everything, what's happening, of course, is your hands are resisting moving. And because they're resisting, they're kind of scraping against each other, and that is making the atoms speed up their movement like we've talked before. And what's happening is it's, like especially when you're running down the court, you don't want to be falling over because your sneakers don't have enough grip on the floor. And that's the whole point about wearing sneakers. All right, well anyway, the problem. Now this is what you have to be thinking about as you're working. How does the amount of friction between a sneaker and a surface compare for different types of sneakers? All right, so you're going to get some different types of sneakers. Spring scale, which is that thing that sometimes you'll see like in the market, supermarket or whatever, where you can put apples in it, see how much everything is massing out. Some paper clips, tape, and the triple balance beam. Procedure. Here's your directions. All right, so it says sneakers are designed to deal with various friction forces, including these. All right, so you have three types of frictions that you need to think about. Think about a basketball player running down the basketball court. Okay, starting friction. This is when you start from a stop position. So that basketball player is standing still, and then he pushes off with his foot to run. And he doesn't want to fall over because his shoe slips, like he's on ice or something, right? Forward stopping friction. This is involved when you come to a forward stop. All right, so the basketball player is running forward, and then he has to actually come real short stop to make the layup or whatever. So he's not even sliding. He just wants to come to a stop from running. Sideways stopping friction. This is involved when you come to a sideways stop. I used to love doing this as a kid. You'd run down the hallway or something. You turn your shoe sideways, and then you'd like put your foot down and slide a little bit. See how far you could slide to a stop. All right, first thing you're going to do is you're going to mass each of the sneakers. So you would balance out your balance beam. You can refer to the other video and Edpuzzle that showed that if you need. And then put the masses. I'm going to give you these little things that have some mass to them to add in each sneaker. So the total mass of the sneaker plus the masses is 1,000 grams. All right, so we're going to see if that's going to work. We might do 500, but I'll tell you when you come into class. And you want to spread the masses out evenly inside the sneaker. That way it's not just going to flip when you do the experiment. All right. Okay, you're going to need the tape for the paper clip to each sneaker, and then attach the spring clip to the paper clip. So you're going to be hooking it around the shoelace, and we're going to do that first on the back of the sneaker. Okay, so it says starting friction, attach the paper clip to the back of the sneaker. So you're going to make sure that you attach that paper clip to the back, and you'll see as you go ahead how that's going to help you. For the forward stopping friction, you're going to attach the paper clip to the front of the sneaker. All right, so this would be where, as you saw earlier, forward stopping friction, that's when the guy's running and he comes to, he wants to just stop from running, okay? Sideways stopping friction, we talked about that. You can imagine me in 7th grade running down the hallway, hopefully no teachers are looking, and I turn my foot sideways to see how far I can slide. Okay, that's you're attaching the paper clip to the side of the sneaker. Again, you can hook it around like the shoelace, but just make sure it's on the side. All right, so you're going to measure starting friction, and you're going to pull the sneaker backward until it starts to move. Okay, so just remember starting friction, you attach the paper clip to the back of the sneaker. Okay, so you're going to pull the sneaker back just to see, as you're using the spring scale, you're going to see it's going to let you pull a little bit and the shoe won't move. You're going to see how many newtons are going to register on that spring scale before it will finally start to move. Okay, now the force necessary to make the sneaker start moving should be equal to the friction force. Okay, again, imagine if you had your hands together and you press them and you start to pull them sideways, they might slip just ever so slightly. That's basically the same force that's holding them together. That's like the rough parts of your hands that don't want to move, and as you begin to pull them apart and they slide, that's the same force you need to overcome the friction, okay? And you record the starting friction in your data table. So let's say you got, I don't know, probably going to give you like a little kid's pink shoe or something. Okay, so you have the pink shoe, you recorded the mass, let's say it was, I don't know, 500 grams. Starting friction. This is when you pulled the spring scale, and the spring scale told you that it was 5 newtons or whatever. Okay, so 5 newtons. Newtons is just a measure of force. Sideways stopping friction, same thing. You turn the shoe sideways, and you went ahead and you attach the paper clip to the side, and you'll see, as you do that, the same deal, okay? And then forward stopping friction, same thing again. This is when you attach the paper clip, forward stopping, attach the paper clip to the front of the sneaker, okay? All right, let's see. So to measure either type of stopping friction, use the spring scale to pull each sneaker at a slow, constant speed. So you don't want to jerk it because you might end up getting a false reading on your scale, okay? But you want to record the stopping friction in the data, and then repeat steps 3 and 4 for the remaining sneakers, okay? So you'll probably have 3 sneakers to work with, so there you go. All right, so that's the experiment part. Now, go to the questions. All right, analyze and conclude. Why is the reading on the spring scale equal to the friction force in each case? Well, if you listened, I might have just given you the answer. I don't know. I guess you'll have to think about it. But after you've done the experiment, you can kind of deduce that. All right, number 2, do you think that using a sneaker with a small amount of mass in it is a fair test of the friction of the sneakers? Consider the fact that sneakers are used with people's feet inside them. Explain your answer. All right, so think about that. Like with the hands together, I was talking about, if you put your hands together very loosely, well, pulling them apart, is it easy? Is it hard? If you press the hands down, like simulating what it would be like if you had your huge, massive feet inside the shoes, pressing down on the floor from gravity, pulling your mass down, would it be harder to move the sneaker? Is something to think about. Okay. Let's see. Let's go to the next question. Why did you pull the sneaker at a slow speed to test for stopping friction? For starting friction, why did you pull a sneaker that wasn't moving? So, for the stopping friction, remember the guy's running and then he wants to stop. Okay, so why did you do that at a slow speed? And then for starting friction, the guy's standing still and he begins to go. Why did you pull a sneaker that wasn't moving? Number 4, which sneaker had the most starting friction? Now you want to think about, of the 3, when you go back to your chart, which sneaker had the most starting friction. So I'm not sure exactly what shoe you'll have. Let's say it's the pink shoe, the orange shoe, and the green shoe, okay? And you'll see the numbers should be different, shouldn't be exactly the same. As you go back to the questions, which one had the most forward stopping friction? All right, so forward stopping friction, again, is going to be this column, okay? So again, the numbers should be different for the pink shoe, the orange shoe, and the green shoe. And of course, sideways stopping friction, let me just show you real quick. Sideways stopping friction, of course, is here, okay? Pink shoe, green shoe, orange shoe, okay? And then let's go to the last question. Can you identify a relationship between the type of sneaker and the type of friction you observed? Okay, this is just a fancy way of saying, can you explain why one type of sneaker had better results? Okay, and that would basically have to do probably with the design of the sneaker. Was there something about the design that was different than the other sneakers, and therefore you can say, that's why. And what do you observe about the sneakers that would cause one to have a better traction than the other? So there you go, exactly. This second question kind of is just a rephrasing of the first one, especially if you're having trouble getting it. And that's pretty much it. So have some fun.